This is Project Zeus, sponsored by ASU SIDSI. Is a look at system infrastructure for collaborative human-robot teaming research. I'm Chloe Dietz.
I'm Jake Gonzales.
Hello, my name is Farah.
Hello, this is Venkateshwaran Srinivasan, aka AJ.
ASU is home to several projects all studying human-robot interaction. We know that humans are good at certain tasks, and that robots are good at certain tasks. We're looking at how humans and robots working together can leverage their strengths. We're looking at how to facilitate collaboration and how the different thought processes affect the outcome of these tasks. Our project in particular uses the UR5 robot arm to work on word puzzles on a whiteboard. One technology that these projects are looking into is a sort of remote server or framework that can collect data from study participants without having to have the volunteers physically inside of the lab. So the initial project proposal had 3 phases. The first phase was to have the robot arm able to finish a word puzzle on a whiteboard. Second phase was to assist a human using explicit commands with some sort of worn interface device. The third phase would be to assist a human autonomously. The client interview revealed an additional set of goals, which was this idea of a server so that volunteers can participate remotely. This has a fairly large scope. At the beginning, we weren't sure what kind of project we were working with. Are we working on AI? Are we working on physically configuring the robot? At one point, he wants to do a mobile app. So where do we start with this? At the beginning of the semester, we said we wanted to have a word puzzle on a whiteboard and also have a server taking input and recording all of our data. As we go on and on through the semester, it's revealed that A, this is a lot of work to do within one semester, and 2, a lot of the requirements are kind of conflicting. We want motion controls, but we also want a mobile phone app. These things don't really tend to go together very well. By the end of the semester, our goal was to be able to use our API to write sentences on a whiteboard. We were moving towards the robot being able to pick up a marker. We decided that was more of a second semester goal. So we also wanted to introduce and calibrate a Kinect camera for the robot to use in distance calculations, stuff like that.
In our project, we use a UR5 robot. It has 3 wrists, and the uppermost wrist connects to a gripper. The gripper is used to hold a marker, and we programmed the robot to write something on the board using Python programming language. At the very end, we were able to complete the code that can write a full word, a full string on the board using the robot. And we also wanted to take this project to the next step, and we introduced the Xbox One Kinect to collect visual information about the environment, and this will be later used to prompt the robot to do something based on this visual information that's collected from the environment. On the software side, we use the URX Python library and the IAI library to achieve our requirements. Both libraries can be accessed online on GitHub. They're open source and completely free to use. So we have completed the code for the string writing API, and our code is very scalable because we can change the sizes of the letters easily by changing a couple of variables. So all the letters are contained within one matrix. Right now it's a 4x4 matrix. We have 3 axes that we're using. We use the x-axis to move the marker away from the board or toward the board. And I'm going to show you right now one example of how we draw the letter K in our string writing API. So initially the marker is placed away from the board, and we place the marker at the bottom left corner of the matrix, and then the robot will move a certain direction to start writing the letter. In this case, the robot moves 1 unit to the left, and then it draws one straight line. Then the robot will draw the remaining vectors to form the letter K. At the very end, the robot will place the marker at the bottom left of the matrix, and then next time we just draw a space, and then we draw the next letter. And that's how we are able to write one full word on the board. The design of the string writing API that we have is simple and very robust. It achieves the requirements that we initially wanted to achieve, and it's scalable. It can draw letters of different sizes. It's very easy to work with for someone to just modify the API, add new characters. We've added the exclamation point as a character to just to actually prove that it can be used for any other writing purposes, not just letters. And the only disadvantage is that we're limited to the Cartesian plane. We don't know how to draw curves and circles right now, but that's something that we would like maybe to do in the future. My biggest takeaways from the project is learning Python and just gaining experience in debugging an industrial robot. I also learned that it's really important to calibrate the robot before we do a lot of technical work with it, and it will prevent a lot of frustration in the future, because we shouldn't skip over simple things and jump into the more difficult stuff.
Let's get on to the results section. So we were able to communicate to the robot using an Ethernet connection. So it connected to the robot and connected to the PC from which all the commands were given to the robot. The entire source code was actually written in the Python language. This was because it had most of the libraries necessary to interact with the robot. We also had to create a detailed documentation on how to use the API and how to set it up, because no such detailed documentation was provided to us. We created a string writing API which enabled the robot to write all the letters and small words. The robotic arm was able to write the word ASU, and it was also able to write the word ABC in one run. We also interacted with the Connect. This gave us a perspective on how it would help us to calibrate the robotic arm itself. These are the results of each sprint. In sprint 1, we set up the project, did the client interview. We also set up the Taiga and the GitHub repositories. In the second sprint, we actually communicated with the robot using an Ethernet cable, and the robot also wrote the word ASU. In the third sprint, we successfully programmed the robot to write all the letters in the alphabet. And then by the end of the fourth sprint, the robotic arm wrote short words on the board, and we were able to interact with the Connect through the PC. This gave us an overview on how we can use it to calibrate the arm, as I mentioned before. Let me just show you the demos of each and every results which we got, and the videos are going to follow right now.
The immediate next step of the project is to finish what we started this semester. Specifically, we want to continue our work with the Microsoft Kinect. So far, we've connected it to a PC and taken visual input. We hope to soon use this visual data to calibrate the UR5. Successfully calibrating the arm will allow it to determine how close it is to the whiteboard. This will help avoid a common problem we faced this semester, where the UR5 did not consistently put the marker on and take it off the board. It ended up pressing too hard and crushed the marker, or didn't move in enough and the marker didn't make contact with the board and we wrote nothing. We also hope the visual input allows us to leave the marker on a table and have the robot pick it up. Until now, someone has had to manually open the UR5's claw and position the marker in its grip for every test run. After that, we want to set up a server for the arm. This would make it so that the arm could be run from anywhere and we would see what it is doing through the Kinect camera. At the moment, another team is working on a GUI to control the robot over a server. A server would allow more devices to access the UR5. Currently, a computer with an Ethernet port is needed, but once the server is established, any computer or smartphone will be able to log online and control the arm. The ultimate goal of Project Athena is to teach the UR5 to solve word puzzles by writing on a whiteboard. So once the arm can reliably pick up a marker and write on the whiteboard, we will look into machine learning techniques to give it problem-solving abilities.